So welcome everyone. My name is Lilac, and I'm one of the organizer of this year's Quantitative Seminar series. And thank you all for joining us in our first meeting this academic year. I'll begin with a land acknowledgement. The University of Washington acknowledged the Coast Salish people of their land, the land which touches the shared water of all band and tribe in the Squamish, Tulalip, and the Maquishnet nations. We also acknowledge that we live and work on the ancestral lands of the Duwamish people, the first people of Seattle. Our speaker today will take questions as we go. Also feel free to drop the question in the Q&A box. Thank you everyone for coming again, and a big thank you to our speaker. Now I'm going to turn it over to Zhang Yue, first year quorum student, to introduce the speaker. Thanks.
Hello everyone, I'm Jiang Yue. I'm a first year quorum student and I will introduce our speaker today. Yunyi Shen is a PhD candidate at MIT in computer science. Although the majority of his work at MIT focus in computer science, machine learning, statistics, but he has a strong interest in quantitative ecology stemming from his ecology master's at UW Medicine. His work in ecology mainly focuses on understanding population and range dynamics, ecological function, and economical values of large carnivores like wolves and jaguars. Yunyi is actually a friend of mine, and we were in the same lab back in Peking University. And can I say that Yunyi was also applied to a quorum program before, but he ended up in MIT. Yeah, and but I can say that he is a really brilliant and amazing researcher, especially in quantitative studies. And he has a lot of collaborators in many fields, even including astronomy. Yeah, and so I'm always amazed by his research ideas when we chat, and I'm sure you will enjoy his talk today. Now I will hand over to our speaker, Yunyi. Now it's your time.
Great. Can everybody hear me okay? Someone gave me a thumbs up. Yes, great. Thank you. Thanks for the opportunity and the really kind introduction. Yes, I applied for QRM once and I didn't get in, and I end up doing statistics later on and coming into MIT. And actually it's kind of unreal for me, especially when I'm staring at my current screen, that I put my affiliation in ECS at MIT, and I'm talking about wolves in the West Great Lake regions. I want to start by saying this is a teamwork with my former advisor, Tim Van Dielen, and one of his former PhD, now a professor at Northland College, Eric Olson. And I also want to say that majority of the work was based on data collected by many people in Wisconsin, especially the DNR researchers, their interns, their summer student, as well as tribe people that actually a lot of the wolf ranges overlap with tribe in Wisconsin. And actually I hope I remember, but I forget to have a land acknowledgement. But hear me, I'm definitely appreciate that we can do research on their tribe lands. So let's directly sort of jump into it. Today I'm gonna talk about wolves, which is not fish, but in Great Lake regions that adjacent. I'm gonna talk about their populations, their range, and some ecological interactions, and hopefully their economics. I did it. All right, start work. Okay, so I hope it's not difficult for me to motivate people that we actually care about wolves, because wolves, they're important. They're keystone species. They're top carnivore, an apex predator, so you can think that they should have some control over those herbivores, especially like deers and other things, and that in turn will have some interaction to our agriculture. And they're also culturally significant, especially for the tribe people. Actually, wolves have some significance in their culture. But they are actually ones basically extinct in the Great Lakes, and they are finally currently have a recovering. So what happened in their success story of this recovery is after a very rapid growth for almost 4 decades and entering the 21st century, especially in the first 10 years, like 2010-ish, the growth is really slowing down and like spark the question of why this is the case. Like, how does this process happen at such a large scale? Like, think about the whole Great Lake regions, or at least the west part of it. There are at least 3 states. Minnesota's here, Wisconsin's here, and Michigan's here. So you can see this slowing in growth at such a large scale. And think about it, if you are thinking about a density dependence, then the density information have to flow in the population. And how does that even possible in such a large scale? Like, I always raise this question. I'm currently sitting in Massachusetts, and I can know there are people in Washington because we have internet. But that's a privilege, not a right. Like, wolves do not have internet. There is no way a Wisconsin wolf would know if there is a wolf in Minnesota or something like that. And then there is another question that is this growth of their population is restricted by prey. Like, this is one of the probably the go-to explanation sometimes when we think about top carnivores. Like, you don't have food, there's no way you grow. Is that the case? And another side of this coin is, does the wolf population self-regulate? Then if they do, then why might that be useful for them and the ecosystem? And actually, I think there is a paper titled, "What is an apex predator?" Actually, they say an apex predator is a predator that self-regulate. Is that the case for wolves? That's basically another question we want to ask. And then when we move a little bit away from how wolf themselves works, we have to think about, okay, how should we interact with wolves? So while removing wolves benefits stakeholders like deer hunters, if you naively apply some theory on predator-prey, then if I remove wolf, then there are more deers for me to hunt. Is that actually the case? So what we do is, with this 4 decades of data from the region, from the West Great Lake regions, and from various other states, we address these questions hopefully quantitatively, and we can give some insight on how this species works and how we should interact with them. So here's a brief outline on today's talk. First of all, gave a brief history of great wolves in the West Great Lake regions, especially focused on the 3 states of state of Minnesota, Wisconsin, and Michigan. And the first part, well, that's the zeros part. I use Python, so it's the zeros part, is the history. And the first part would be, we talk about the large-scale density dependence. It's basically answer the question why they finally start to slow down. And why can that be understood as an expanding frontier meets some habitat boundary problem. Then we move on to what's happening inside of their habitat, and especially their interaction with their prey, especially in Wisconsin, Minnesota, and Michigan. Those are white-tailed deers. And we can see, hopefully I can convince you that territoriality of wolves could induce a self-regulation, and that self-regulation provides some evolutionary benefits by reducing noise in the population size when you consider various sources of stochasticities in their population dynamics. And then in the last part, we're going to a little bit more statsy study that we did on how answer the question how we should interact with them. We applied some causal inference technique on whether wolf hunting policy could affect on deer hunting, like whether kill wolf would benefit deer hunters. All right, let's jump into the first part. First of all, gave a brief history of wolf recovery in the Great Lake regions, or West Great Lake regions in the United States. When I say West Great Lake regions, I mean these 3 states. This is a quick map about their spatial adjacencies. Actually, one thing I want to mention, and I'll go back to this in the third part of the talk, is that these boundaries between Wisconsin and Minnesota, and boundary between Wisconsin and Michigan Upper Peninsula, if you can see my mouse, they are almost human-made. They are not natural boundaries. which means like you can sort of assume that nature are continuous like along these boundaries, and that actually provide us some very good opportunities of speaking about some policy implications. Okay, let me give you a brief timeline about what happened to wolves in this region so that we can understand why what kind of questions we're asking and trying to answer. So first, like before European settlement, wolves are in their historical range. Historical range basically means they're everywhere across the state, so long as there's no water. They can go wherever. There are plenty of deer there so that they can eat. But in the 1800s, there are uncontrolled huntings, bounties, and extirpation. So what happened at that time, especially in, I'm a little bit unsure about Minnesota, about Michigan, but in Minnesota and Wisconsin, is people first have uncontrolled hunting, or actually commercial huntings of deers, and then they basically took out all the deers. Then wolves started starving, and they started attack livestock, and people think, oh no, they're attacking our livestock, so we're gonna kill them all. And that actually happened. People basically kill all the wolves by either shooting them or poison them. Now let's fast forward to 1973. It's a key year because that's the year where Endangered Species Act started to take place in the US in federal level. And 1 year after that, the wolf is listed as an endangered species, so there is no more bounties and huntings or poisoning or whatsoever. That will allow them to actually recover from the previous almost local extinction in these 3 states until 2012, whereas something interesting happened, is in that year, wolves are briefly delisted from the Endangered Species Act endangered species list. And interestingly, in that one day, on the day that wolf is officially delisted, Wisconsin, the former administration passed a law that's saying, okay, if the wolf is delisted from the Endangered Species Act list, we have to hold a hunting season. That's why in 2012, Wisconsin has this law and it was triggered. So there is a hunting season in Wisconsin, but not adjacency state. And that gave us some interesting opportunities later on. Well, I'll just show you a map because we're ecologists, we like maps, so that it will give you a rough idea of how they expand their ranges. So I believe that the first pair of wolves go into Minnesota from, I believe, Ontario in probably 1980, soon after the Endangered Species Act. And then they briefly expand to south and then entered Wisconsin and then expand south and east. So purple is the first probably 10 years, and blue they expand here, and green they expand here and enter the Wisconsin, and then orange they start to occupy a large chunk of Wisconsin land, and now we're in this red area, and the base map is a habitat suitability from Gentroff et al. In 2022, so they're sort of occupying their suitable habitat. So let's go into the first part, because we just finished the zeros part. It's about how their expanding frontier meets habitat boundary, what gives you an illusion that they looks like a logistic growth. It's a mechanism of large-scale density dependence for wolves without triggering some interesting information puzzles. So before I go into whether there is a density dependency or how density dependent actually happens, we first should look at whether there looks like to have a density dependence to start with. So here I show you a total population growth of wolves in Wisconsin. I want to mention that this population is by numerous effort that people actually go stalking wolves and count them in winters when they are easier. And actually that's easier in Wisconsin, much easier in Wisconsin compared to probably in Washington, because Wisconsin's just so flat. So x-axis is time, is year. Hopefully that's straightforward. And y-axis is the so-called winter minimum count, which consider as a good indice of the total population of wolves in Wisconsin. And each of this circle dot is their growth, their population as a function of time. And I fit a simple logistic growth as this solid line. And as you can see, until 2012, it fits pretty well. And I can extrapolate using fitting this logistic curve using data only before 2012. Why only before 2012 is because 2012 has a hunting season, and that sort of messed up the dynamic. But how do I validate it? If you think about hunting, one way to think about it is it takes away individuals. Another way to think about it is it reset the dynamic to an early stage, to an early initial point. So one way to validate this extrapolation is let's move the later after hunting population growth back in time to somewhere you have a similar initial state that is roughly around 2011. It roughly aligned with the population size post 2 years of hunting in 2015. And we can see that a logistic growth could actually extrapolate and predict the population growth in this reset curve. And that also means we fit a carrying capacity, and a carrying capacity is sort of aligned with literature values based on the available habitat amount. And now I'm going to show you that hopefully established in a large scale that it looks like we have a density dependent and we have a carrying capacity, but is that also the case in a more local scale? So the question is whether in any local place that the local density looks roughly the same or at least same on average. The way we test this is people in Wisconsin, especially DNR people, not only go stalk wolves to count their population, they actually tried all their best to not tag, but color at least one wolf in each pack so that you have an idea of their range. And these two things are measured independently rather than inferred from each other. In some state, these are inferred. Like I remember probably in California or in other states that they infer population from an occupancy model using their range. And I want to stress that this is not the case in Wisconsin. We measure range and population separately. And you can see the population and the range measured in all these years fall in almost a perfect line. This is actually the first time I see an R-score 0.99 in the wild. It's literally in the wild. And even including this post-hunting years. That hopefully can give you an idea that within their range, their local density, or at least on average, is sort of a constant. So what that means is we see a equilibrium that stemmed from density dependent in both local and on a landscape scale. So let's think about how this could happen. Assume that a population is completely well mixed in the sense that their individuals can go wherever they want. And there is no spatial the space is homogeneous. There is no heterogeneity in space. And then if you see a logistic growth, then you can say, oh, it comes from this very familiar logistic growth differential equation, like the change rate of population equals to some intrinsic growth rate times the population size times we call a density dependent curve, a density dependent term, and a carrying capacity. So that if you have a population size roughly around the carrying capacity, you are no longer growing, and if you exceed the carrying capacity, you start to decline. But then we usually attribute this density dependent term to say pre-supply. If you were thinking about plants, it might be light, it can be water. But if you take a step back and think about what's the common thing about this mechanism we usually talk about is they are accessible local information. Think about I'm a wolf, or I'm just a human. I'm roaming around on the landscape. It is very easy for me to tell if there are enough deer. If my hunting success is just super low, then yeah, I have the information that there's no deer. then the population has the information that, okay, probably we're close to carrying capacity. And that information eventually translate into, okay, higher lower survival rate and higher mortality. But if you think about a large-scale space as a resource, then you run into this trouble. Then you run into this information puzzle. Like wolves has no internet, no phones, no map, unlike us. If I'm a wolf in central Wisconsin, it's probably not too difficult for me to tell, well, there's no food here. I didn't see deer. I didn't see other things I want to eat. Maybe I should go to the dumpster and eat garbage. But it is very hard for it to know if there is wolf in the north or if there is available habitat in the north. Because in their lifetime, unless it is a transient wolf, in a territory wolf, it's very hard for it to actually travel there and travel back to see if there's other food there. And that's the same thing for north. Then basically, almost for majority of the individuals, there is no information about this overall population size or overall density. So here raised this information puzzle. I raised a couple times that the logistics are different in a very large landscape scale and in a local scale or in a well-mixed population. Lie in whether you have access to information about your population density. So in the usual logistic growth that we are familiar with, the population have access to local information, like pre-supply is easy to tell. But the population usually don't have access to global information, that there is no way that they can tell whether there are still available unoccupied habitat remains on the landscape everywhere. There's no way for a wolf in Wisconsin to tell whether there is habitat in Washington, let's say. Then why this speed up and slow down happen? If we're thinking about density dependent, if there is any dependency, there must be information flow, and that must happen. So we have this sense that dispersal has to be one of the key things to consider. But how? Well, if you imagine yourself as a wolf, then how do you make a decision? I'll make a decision like, I'll disperse. If there is food in front of me, but there is no wolf preempting me, then I'll go. And I'll become the expanding frontier. So if you just build this in to a dynamic model, as R.A. Fisher and Kolmogorov, if you do statistics, these are just two very big names, and apparently they study population dynamics for whatever reason. If you write down a partial differential equation that including a local density growth, local density dependent growth, if you cover this part, this just looks like logistic growth, and having a dispersal term. Then you can see sort of this kind of logistic growth without the information to flow globally. So how? In the simplest case, let's consider you have a rectangular habitat and your population start at the lower bottom edge of this habitat. What's going to happen is the population is going to expand because there are dispersal, and you have this dispersal frontier. When it starts to expand out, the length of this dispersal frontier actually elongate at the early stage, and remains a little bit constant for a while, and until it clashes with other boundary, then the length of this expansion frontier start to shrink. And if you calculate the population size by basically sum up the density, what you will see is as time goes by, this our model time is not real time. You will really actually see something looks like logistic, but this one is purely spatial, as you don't need the population to access the information like the total number of individuals divided by the total area. There is nothing in the model needs that, in this Fisher KPP model needs that. but still it can simply resemble this logistic growth by this geographic, not geographic, but this geometric frontier meets boundary mechanism. And that would also explain our observed linear relationship between relative range, between range and population. Here I use relative as normalized by the available habitat and available by the carrying capacity. So hopefully this will give you a sense that a simple model with dispersion actually could give you something look like logistic growth, despite the population is not well mixed in space. Well, that actually give you a more interesting behavior than a simple logistic growth. Yes, so I don't know how much you heard about a Lee effect, but basically this means an Lee effect is when the population shows positive density dependent when the density is really low. And this type of effect in a simple Fisher KPP model, you will have a simple geometric explanation when there is a habitat corridor. When in this example that I put a corridor here in the lower half of this rectangular habitat, what will happen is in the initial stage of the expansion that the frontier cannot really expand because there is no habitat. The habitat is really narrow. And then the population has to expand and go into this larger habitat to start really speeding up the growth. So what you will see in the total population growth curve is a very elongated early stage that is a signature of an Ali effect growth. And then suddenly you see a speed up of the growth because the population expand into the larger habitat. And still you will see this almost linear range to population curve. So that actually this interesting positive, seemingly positive density dependent might come from a simple geometric effect. And we also want to test it in Wisconsin. So we want to fit this simple model using Wisconsin data. So what do we do here? Is we gave it a literature value of a habitat map from Genschop, which is not from our own study. And we feed it that map as the available habitat, and also feed it the growth curve. We just use the growth curve to fit the time scale and the equilibrium density within their habitat, and without using actual distribution of the wolves we used. So basically only a map other people draw and the growth curve. So we can resemble the expansion from northwest to southeast in Wisconsin, and also this almost linear range to population map and this almost logistic growth curve. Well, let's take a step back. What did I do here? I actually cheated a little bit. I actually assumed some local density dependence. Despite this solve the problem, like I don't need the model to take in a global density as an input, but I still assume some local density dependency. So what does that actually mean in this ecosystem? So that will give us a primer on why we actually did the second part, is we looked into how inside habitat boundary, within habitat, how come the wolf seems to have some density dependency. And we want to say that it looks like, at least in Wisconsin, but might not be Washington, the spacing behavior and population self-regulation of wolves would explain what's going on inside their habitat. So that's basically the question, what happened in the middle of habitat? We just discussed how large-scale regulation occur by interaction of dispersal frontier and habitat boundary, and then how regulation happened in the middle of habitat is still unsolved. And here are at least two main hypotheses that we want to look at. The first is, okay, pre-regulation. There are only this many prey that you can eat, so you can't have a very large density of wolves. Or there might be some self-regulation. For instance, wolves just want to stay away with each other. So if we want to think about self-regulation or test whether there are self-regulation due to territoriality, we should take a look of their spacing behavior among different packs. And luckily, at least in Wisconsin, Oregon, and here, there in your place in Washington, that people actually track wolves. So you actually know where packs are. By doing that, we can actually calculate. For instance, you have a pack here and you have a pack here. Then we can calculate their distance. For any pack, we can calculate the nearest neighbor distance. So that's basically the space that at least looks like the distance they want to maintain. And we can see whether that actually carry through along a lot of different locations. So here I show the x-axis is time, 2004 and until 2011 before hunting, and y-axis is just the nearest neighborhood distance among centroid of packs I just described. And first, it looks like there are some lower bound, or it is very persist among Wisconsin from 2004 until 2011. And we also have other survey, which is rendezvous site. Basically, we know their real-time location. And we also see sort of this almost 15-kilometer spacing among packs seems to be pretty universal in Wisconsin. And I compared it with, remember in the first part, we have that almost perfect linear regression that will gives you a stable local density dependency, local density. And if you assume that the density was achieved by packing circles in the space, then you can translate that density into nearest neighbor distances, and that's this dashed line. So basically, the distance we saw align quite well with what with the regression approach we see in calculating their density or their spacing, the space they want to maintain. And I mean, if we thinking about linking density to their distance, that density, like I mentioned in the first part, is not the only density people looked at in the past. Actually, Maizière 1994, who did a simple regression on the amount of prey, well, the density of wolves as a function of the amount of prey, and he found there is a plateau density that basically getting more prey will not really increase their density, and that density is this lower dashed line, which sort of aligns pretty well with the lower quantiles if we see in Wisconsin. And apparently that seems to sort of aligned with what we see in German after doing the same treatment. Besides, there are some outliers here and there in different years, and Oregon, especially in the later stage of their wolf recovery. But interestingly, that's not the case in Washington, and I don't really understand what's going on in Washington, that wolves seems to hate each other more and want to stay away with each other for longer and for further. If someone has the intuition on what's going on in Washington, please let me know. But at least I want to say that there are 3 or some other states that basically follow this pattern that we see a almost 15-kilometer spacing that they want to maintain. Then let's try to give a test on whether this kind of spacing related to prey density. If you believe, or based on not maximum, but optimal foraging theory, what should happen is when you have higher deer density, you don't need to explore a lot of space so that you can feed yourself. Then with higher deer density, what should happen if deer is the limiting factor is the distance among packs should be shrinking. And that should explain a large amount of the variance in this distance behavior. So in Wisconsin, actually, we have some estimate of deer density at each county. And then from there, we can make this simple curve that x-axis is the deer density in that pack's location. And we can plot the y-axis as the distance the distance to nearest centroid of that PAX location. And surprisingly, we see a very mild positive dependency between distance to nearest centroid and deer density, which sort of, it's not the prediction of a optimal foraging theory and deer limitation or prey limitation. And also that actually explains very limited amount of variance in what we see. Actually, if you just observe these parts that with relatively okay, reasonable deer density, it's almost a flat line, and maybe some of the point here actually driven this positive correlation. So here it looks like, at least in Wisconsin, that what we see is more like a self-regulation among wolves instead of limited by deer. Then here's a question: then why this should be the case? Like, is there any benefit a wolf regulate themselves? Actually, yes. If you go back to classic predator-prey theory, back even into MacArthur time, if you read a 1975 paper, if I remember, that he actually say, yeah, if the predator has self-regulation, then the predator-prey system would be more stable. But what they mean by more stable, if you're familiar with the stability analysis of ODEs, of dynamic systems, that means if you linearize your dynamic system around the equilibrium, you got a linearized dynamic system, and that dynamic system has very large negative eigenvalues, so that it will spend very least amount of time to go back to equilibrium if you gave it a small perturbation around it. And here, if you do that simple simulation with a for a predator-prey system, a logical terror system, with some simple predator regulation, you will see, oh yeah, without sacrificing on average population density of predator, you will see it suppress all these oscillation behavior. And x-axis is our simulated time, and y-axis is population density. And red lines are simulated predators. Then the red line are simulated with a predator density dependence, and you can see there's no such oscillation. And if you look at in the phase space, it will just go into equilibrium super fast and without going into the spiral. But okay, what that actually means in the population sense, like the stability is a little bit more like a mathematical behavior of this model, and how does that actually translate to what they mean to the population? It's a little bit unclear, at least to me. But there is a way to translate that. If you think about there are noise actually in the system. The prey, well, the environment has fluctuations, and that means the carrying capacity of prey has fluctuations. And all of these two species, predator or prey, they have demographic stochasticities. That means they have fluctuations in the dynamic. So let's take them into account and see what that would do. So once you start to incorporate the stochasticities in the model, which will translate an ordinary differential equation into a stochastic differential equation, and your the population dynamics will look like more wiggly because there are noise, and you will see, okay, what the stability actually means when there are stochasticity is you will have a much smaller noise. So all the gray curves are without predator density dependence, and all the red curves are with predator density dependent. So if you observe that the predator density as a function of time with density dependent, you will see, okay, it really don't like oscillate a lot. It's around 2. But despite with the similar average without a density dependent, what you will see is you have this large variance. And what that also means is you have a higher chance, the predator will have a higher chance to extinct if you have a higher variance in your population dynamics as a function of time. So what this will do that will actually gives you a bias variance trade-off type of situation. If I'm a statistician, I like bias variance trade-off. So as a function of carrying capacity, which physically probably means the nearest distance that they can tolerate when they're on the landscape. As a function of that, you can think about there are two things that you want to simultaneously maximize. You want to maximize the average population size so that on average, the predator has higher population density. And the other thing you want to measure is you want to lower noise, which means higher precision. I define precision as 1 over standard deviation. So an ideal population will have very high average population size and very low variance. That means you are really stable at your mean population size, which is also high. But they are contradicting to each other as a function of spacing. Because with high carrying capacity, basically means you can tolerate each other closer. What will happen is you probably have higher average population size, but lower precision. And the other way around, if you have a lower carrying capacity, what's going to happen is, okay, the population has very low noise, but can have also very low population size. I'm sorry, my Slack is raining. All right. Hopefully you had a sense on how wolves work, also with deer. Now let's start think about how we should interact with them. And this last chapter is more about more statsy. It's basically we answer the question: does hunting wolves benefit deer hunters? And I want to mention this is with help from Eric Xia, which is a PhD student here at MIT. We did some causal inference here. So, as we had a sense in the previous couple half an hour, that wolves are returned to the West Great Lake regions, and people hunt deer. That's another new fact. People just hunt deer. And now there is another competitor to hunters. Wolves coming back, and wolves also hunt deer. Then some hunters will naively apply predator-prey theory. If I have a competitor, then I must be less successful. Then the naive application of predator-prey theory would suggest hunting wolf is beneficial to deer hunting. Well, when we want to ask the question, is that true? But that's basically asking what's the effect of wolf recolonization and wolf hunting on deer harvest? We're asking a question about causal effect. But what does that mean? Let's take a step back, thinking about what the question we're trying to answer and how ideally we can answer it. Let's imagine there are two alternative universes. Let's think about what causal effect even means. Suppose there are two alternative universes, a world with wolf hunting, and we measure the deer harvest in County 1, County 2, and County 3 in that world to be 100, 80, and 50. And there is another world, there is no wolf hunting. And we measure the County 1, County 2, County 3's harvest at 50, 10, 80. And now we can calculate the individual effect of wolf hunting at each county because we observe both worlds. And then you can calculate these differences as the definition of the effect. Then if you want average, you take average of the third column. But the fundamental problem of causal inference is that there is no alternative universe we can do. If there is hunting in County 1, if there is no hunting, we cannot go back in time and hunt there. Then that means two of these entries must be missing, and there's no way we can calculate the individual effect of wolf hunting. Then there's no way we can calculate the average this way. But if there are, you probably heard that randomized controlled trial is the gold standard of establishing causal effect, but that's why that is the case. Because if the assignment of which county you gave hunting is random, then you can show that the average of the average deer harvest with wolf hunting, you can estimate that by taking average of all the wolves, all the counties with wolf hunting, and similar thing that you can do that average. You can do that average in all the counties without wolf hunting, and that will give you the right estimate of the average deer harvest in counties with wolf hunting and without wolf hunting. Then you can estimate the average individual effect by taking the difference, because expectation is linear to linear expectation. You can exchange order of expectation and taking difference. But that's also usually not the case for wildlife management. So the best hope we have is if we have some natural experiment. There's no way we can do randomized control trial. But the blessing of what we have is policies might have a border that are not ecologically meaningful. How that would help us is if we assume nature does not jump, then nature does not jump, but policy jumps, which means we can impute both worlds at the border, at the policy border, from the left of the policy border and the right of the policy border, because all other things are continuous there. So here is a graphical explanation of that idea. Let's think a one-dimensional world. There is a region without wolf hunting, and there is a region with wolf hunting. And there is a boundary saying here, left hand of this boundary we cannot hunt, and right side we can hunt. And then you can measure the deer harvest, say, per capita at each of these locations, and using distance to this boundary as a predictor. And then what we can see is we'll have two curves from using data only from the left and using data only from the right. And if there is an effect, because your policy changes at the border and other things are all continuous, what you can do is you can extrapolate this a little bit. You can extrapolate data from right-hand side a little bit and predict what deer harvest would be at the border if there is wolf hunting. And similarly, you can predict the deer harvest if there is hunting at the border. And now you can take the difference and you can call that the causal effect of wolf hunting policy at the border. This is called a regression discontinuity design with different natural experiment. And you can think about if there is a natural border, and then you can do this using the distance to the border as the so-called running variable, and you can test if there is a jump. So the first natural experiment, which is weaker, because we usually don't use time as natural experiment because it can be confounded with the other things also happening in time. But here, well, that can still give us some insight. So we can use wolf recolonization as a natural experiment, because wolf recolonize at different time, this is deer management unit in Wisconsin. And what we can do is align each deer management unit in time using when wolf colonized them as year 0. And here is the distribution of deer harvest per capita at that deer management unit as a function of wolf year. Left-hand side would be there is no wolf, and year 0 is the wolf first landed there, and right-hand side when there has wolf. So clearly you didn't see a jump here. That probably says, okay, the wolf recolonization does not seems to have a strong effect, at least not immediately, on deer harvest. That answer partially answer the question whether there is an effect of wolf recolonization. And what happened, as we mentioned in the early part of the talk, that there are actually an interesting law happening in 2012 that forced Wisconsin to have a wolf harvest, but not in other adjacent state. That in these couple years, we have a natural experiment in space that in 2012, all these blue squares are the years that allowed lethal control, but not hunting. And yellow squares are the years allowed hunting and lethal control. As you can see, the only difference between Wisconsin, Minnesota, Michigan Upper Peninsula here is whether you allowed hunting on top of lethal control. And similarly for 2014. And that's also the case for between Wisconsin and Minnesota, that cross the border, the only difference is whether you allow lethal control. That would give us an opportunity to test if there is a causal effect of hunting on top of lethal control by comparing Michigan Upper Peninsula and Wisconsin, use Wisconsin data to extrapolate what's the deer harvest at the border. That will represent with wolf hunting. And you can do that with Michigan and use that to predict deer harvest at the border as if it's from the world without hunting. Similarly, you can test the effect of lethal control using data from Minnesota and Wisconsin. So what we'll do is for a grid, for a bunch of points along the border, we run a regression and to using distance to the border and other environmental variables as control to see if there is a big jump, as we see in that one-dimensional example, whether there is a effect of wolf harvest. So maybe it's a little bit hard to say, but I can tell you, as we didn't find any significant point. All these points are insignificant. So after adjustment of the p-values, so we didn't really find a causal effect of wolf harvest on deer hunting, on deer hunter success. That's also the case for lethal control other than harvest, to deer harvest by comparing Minnesota and Wisconsin. So basically, we find no particular effect of wolf harvest policies. So what might be going on? It might be just lack of power. That's totally possible. And there might be just actually no effect because, as we said, wolves are territorial. So the predator-prey is actually very stable. So you won't really see the density of deer surge when you take some wolf out. And also, deer hunter have type 2 functional response. Like as the deer population goes large, the number of deer you can harvest levels off. And even if hunting wolf really increased deer density, it's probably still in that plateau region. So you didn't really see that effect. As a recap, so today we talked about after fast growth for decades, wolf growth are slowing down. How does this happen? Our theory is this is by frontier clash with habitat boundary, so you cannot disperse any further. And do wolf populations self-regulate? Why might this be useful for them and the ecosystem? Our answer is, seems they do. It will suppress noise in population size and prevent them from extinction. Will removing wolf benefit stakeholders like a deer hunter? Seems no, since they might just be too many deers and too little wolves anyway. I hope these papers will be up soon, but there is an early draft for the first paper on arXiv. If you want to see a draft or something, or want to collaborate, just feel free to email me at this email address, and I'm happy to take any questions. Please.
Awesome. Thank you so much for the great talk. We've got a couple more minutes here. So if anybody has any questions, feel free. Write them in the Q&A box and we can answer them. Otherwise, I've got potentially one.
Yes.
And if there's have you thought about trying to look between the border of those states and Canada? I know you were saying that the wolves were coming in potentially from Ontario, but if there's some sort of difference between the hunting regulations there, or if it's kind of the same effect that you see.
That's actually a great question. I mean, not for Wisconsin, because if I show you the map here, let me see which map is the best. Probably this map is, no. Oh, okay, this map is probably the best. Wisconsin does not have a border with Canada.
Mm-hmm.
And the other two states has border with Canada, but they don't really have hunting at this couple years. But there might be hunting in Canada, I'm unsure, and that's actually a very good proposal. We should ask Ontario people. The quick answer is not yet, especially because the place where have hunting does not share border with Canada, but there might be a potential there. Yes, thanks.
Any other questions? If no, thank you again for a great talk. And if anybody does have questions they don't feel comfortable answering here, Yunyi did have their email up and you can reach out to them. But otherwise, thank you all for a great first Quant Sem of 2024. And we will have a talk next week, same time. We're going to be hearing from Caitlin Magel about models facilitating comparison of the social ecological trade-offs among Puget Sound management alternatives. Thank you, everybody, and have a great weekend.
Bye.